my sort of key points from the last day, and I hope that's been a reasonably useful summary. So now moving on to this morning's session. We'll start off with another technical session on satellite imagery, remote sensing and geospatial data. We'll then break for morning tea, and after morning tea we'll explore the challenges and the progress that's been made in the area of skills, training and capacity building. So I'll now hand over to Greg Scott from the UN Statistical Division, who will moderate the next session. Thanks, Greg, and thank you.
Thank you, Trevor. Good morning, ladies and gentlemen, and welcome to day 2 of our very important conference. You don't want to hear me this morning, so I'm going to be very, very brief. We have 5 very, very good speakers with us this morning, and also our chair of our task team on satellite imagery for remote sensing, Dr. Su-Ming Tam, and I'm going to ask him to open, and then we will follow by our presenters, and after that we will take a series of questions. I'm promising as a mission being on a mission so that we have some time for that. So please, Su-Ming, over to you. Thank you.
And there are quite a number of challenges, and we had a chat among ourselves on, what are the things that were challenging us when we're doing our pilot projects. They are in these 4 broad areas. One is that, this is another point that Trevor made, that big data, even though many of the big data is available free of charge, certainly in the case of satellite imagery, they are available free of charge. It doesn't mean there is no cost involved in processing the data. In fact, there's a lot of work that is required to put your data in a form that is suitable for analysis. And in the case of Australia, we're trying to get a small amount of big data, and because we're doing it for the first time, it took us about 8 months or something before we were able to actually put the data in a format that is useful for our own analysis. So gathering the ground truth data is another element that was seen to be quite challenging, because the data that most people use, and we heard yesterday from Global Pulse and others, that they're using official statistics to calibrate. But when we're in the official statistics production area, we need data to calibrate the big data, and sometimes we don't have that data. So we have to talk to other partners in Australia to get that ground truth data. And getting the data at the right level of granularity is also a challenge too. So in the case of satellite imagery data, you have data available at the pixel level, but generally the data available from statistical offices are related to a higher level, like, a collection district or administrative boundary, so they don't align quite well. And finally, after you gather the data, you still need to, turn that set of data into outputs. And this is where the black box occurs. This is where the magic occurs. Now, in a lot of cases, some of the methods have to be developed, and I think some of the methods are already available in the literature. Others are available in machine learning sort of literature. So the challenge for us is to look at which method is actually suitable for our own set of data. Do we need to adapt it, or do we need to adopt it, or do we need to develop new algorithms? Now, in our case, in the case of Australia, we're actually developing some new algorithms. I think in some of the applications, they're using some existing methods. So in the case of using existing methods, you have to learn the method and so on. And finally, the challenge is about priority and resourcing. Not everyone in the office, even in the case of Australia, is convinced that big data is the way to go. So it's a bit of challenge. And I was speaking to Pete from Statistics Netherlands yesterday. He said that they have got a method developed to publish traffic statistics using sensors. The method was already developed, but it took them 6 months to convince the subject matter people that this is a better way to go. So.
Thank you, Su-Ming. Much appreciated. What I'd like to now do is call on our first detailed technical presentation, and this is going to be from Dr. Arnold Decker, who's the director of the Earth Observation Informatics Future Science platform in CSIRO in Australia, which is the Commonwealth Scientific Industrial Research Organisation. Arnold, the floor is yours.
This is an overview of some of the satellite programs that are currently active. Only 3 satellites are currently used, as far as I can see, by the Global Working Group. So there's an underutilization of what is in space. There is much more available. The improvements in Earth observation sensors fall into 4 categories. Higher spatial resolution. It used to be 30 meter with Landsat. It will be 10 meter with Sentinel-2 for the next 15 years, will be publicly available. Higher spatial resolution than 10 meters is currently commercially available. Higher spectral resolution. The number of wavelength bands, be it visible, nearby infrared, or synthetic aperture, or in thermal wavelength bands, are going to increase. And recently I heard a statistician say, I'm not interested in spectral bands. Well, actually you are very interested, because you get less confusion per pixel, per crop type, per condition. More variables can be measured. Better identification, better discrimination, higher temporal resolution. So you're going to get more images faster. And it's going up 5-10-fold per year in the next few years. And higher radiometric resolution. That's the sensitivity of the sensors, which means higher accuracy and precision. So these are things that are important for statistics. So this is an example of a subtidal area at 30-meter resolution. The current standard with Landsat at 10-meter resolution, which will become the standard with Sentinel-2 from the European Space Agency. And commercial sensors going down to 1.6 meter spatial resolution. Now the next slide shows you an island in an intertidal estuary where we mapped the plant species. And I won't go into detail on the plant species, but this is 30-meter resolution, 10 meter, 2.6 meter, and 1.6 meter. Which one has more information? Which one do you rely on more? Which one do you want to use for official statistics? So this is the future, and it's going rapidly. But going from 30 meters to 10-meter resolution is a 10-fold increase in data. Do your own sums. So this is the way a satellite images, and you see a lot of spectral bands there. It's not just blue, green, red, what humans see. There's many more bands. In the future, we will have sensors with 100 spectral bands, as compared to what we see with 3. Okay? So the future is much more information, but much more data, and we have to translate it into information. And this is our challenge. This is a challenge of the Earth observation community, of the GEO community, the group on Earth observations, the challenge for the statistical agencies.
Thanks, Arnold. Much appreciated. And Arnold has very concisely, and I apologise for condensing your time, provided a really good synopsis of remote sensing data sources and the evolution and where this is heading. So what I'd like to do now is call on Dr. Andreas Poitgeter from the University of Queensland in Australia to actually give us an application of this in crop production. So without further ado, Andreas, over to you.
Thank you. The first example is from Dr. David Rubel from Stanford University. And very briefly, there's papers on this, all of this, I'm going to show you now. They've used the APSIM, which is an Australian dynamic scale model, the crop simulation model. They've integrated that with Landsat satellite imagery, and they update the leaf area index parameter in the crop model then to predict maize yields in states of the USA. And there you can see the point scale model, they simulated at a few points across those 4 states, but using satellite imagery, then they can extrapolate all of these then to a pixel basis, 30 meter by meter, 30 meter pixel basis across the larger regions. The other advantage of this is also the crop biophysical model. You can use that then to, even before flowering and emphasis, to predict, get an indication of what a likely crop yield is. The second example there is from Inbal Rashev. She's working with GeoGLAM. She's responsible for those reports in GeoGLAM, Global Agricultural Monitoring Systems and Reports. And as the previous speaker also mentioned, it's very important to have those connections and people starting to use this technology globally. Example here is, although it looks a little bit busy, on the right-hand side here, this graph, the data, the blue line there is just the data, the NDVI from the satellites that she uses, and then she incorporated temperature data from climate stations, and she predicted yields for USA and China. So the temperature data is converted into growing degree days, which drives the crop. And for China, see, just the forecast within 6% of final yields 2 to 3 months prior to harvest. The third example here is from Nathaniel Newlands, which I was co-author on this paper, and they've developed very similar approaches to us in Australia by incorporating a biophysical crop model with satellite imagery and some very high-end Bayesian statistics in this. So they've used this tool, which is online available. They've predicted spring wheat and barley in Canada with various success. In this case, there's still some room for improvement. The next few slides, and hopefully, and that's where I will end, is my work, which I've been doing for the last 17 years in Australia. And we've developed a regional scale commodity forecasting framework, which incorporates actual data, biophysical crop models, satellite data, and crowdsourcing to train and validate the data at the pixel scale. And I'm very excited about all the latest satellites and satellite data that will be available to us in Australia. As Arnold has shown, specifically the temperature data, which can also be incorporated at a later stage.
Thank you, Andreas. Much appreciated. And what we're going to do now is move from Australia around to another part of the world and go to Colombia. And I'd like to invite up Ms. Sandra Rodriguez, who's the coordinator of the Research and Development Group in the Geostatistical Division in the National Administration Department of Statistics of Colombia, DANE. And she's going to talk to us about the use of satellite remote sensed information in terms of land use and land cover statistics. Over to you, Sandra. Thank you.
With this project, we want to explore the usefulness of big data from satellite land images for the updating and improvement of demographic and geographic statistic information. We hope we can calculate an indicator that shows the urban agglomeration degree by using satellite images and population data from metropolitan areas. This project will show whether it is possible to use this indicator as a measure of sustainable land use. This indicator could provide additional information to the framework for the implementation of healthcare policies, policies resolving food access problems, and climate change policies. The following are the steps to get the expected results. Data collection. At this stage, the project first needs to search satellite images and collect the information necessary for the project's development. Also, the project can use population data that DANE already has. Both the satellite images and the population data were taken in 2005, 2010, and 2015. Change detection. Change detection is a process when one identifies differences in the states of an object or phenomenon by observing it at different times. In this project, this process starts with the satellite image pre-processing, then the land use and land cover classification is made, and finally, the accuracy of this classification is checked. Rate calculation. The land consumption rate is calculated with the data from satellite image classification, and the population growth rate is calculated with the population data, which was taken from the 2005 census and the population projections of 2010 and 2015. Indicator calculation. This indicator is a ratio between the land consumption and population growth rate. The Landsat images used for the project were downloaded from the United States Geological Survey Earth Explorer website. The image acquisition process was done under these criteria. The images have to be easily available. The images have to have less than 10% cloud cover. The images have to be taken at the same time of the year. The images have to cover the whole metropolitan area. And the images have to have similar spectral bands.
Thank you, Sandra, much appreciated. We're now going to take another shift in our presentations, and I'm going to ask Mr. Patrick Dunnigan, who's a Strategic Partnerships Manager at Google, to come and talk to us. And he's going to talk about global economic transparency and how Google is working in new frontiers in remote sensing. So Patrick, the floor is yours. Thank you.
Thank you. So this is the Burj Khalifa, so we're actually taking full motion video from space with our sensor right now. Because of how we built the system, we can point and shoot, and then we're leveraging commercial off-the-shelf technology as opposed to government technology, which allows us to build it for a much lower price point. So this is more just of a cool side capability of our system. If you go to the next slide, what the system really enables us to do is collect imagery at a high cadence. And what we're doing is we're pointing the satellites right now toward economically significant sites around the world, or economic choke points, so major cities, ports, and the like. So you can see with the, I don't know if you can see it very well, but this is a series of images collected over a period of time. And as we continue to launch more satellites, by the end of next year, we will be able to track hundreds and thousands of sites around the world on a daily or weekly cadence. And you can see there's a lot of, even without going into the spectral bands, there's a lot of very interesting information in these slides right now. And so you can see cars, shipping containers, trains, oil tanks, and the like, just with the naked eye. And so what Google has done already is they've built out some systems to detect features in YouTube and Street View and image search and the like. And so we've plugged our imagery into those, and we have some interesting early results. If you go to the next slide, please. So what you're seeing here is a Toyota import lot in the port of Long Beach. And so we're detecting the cars that are visible in that lot, which are interesting, for a lot of companies, as well as if you're trying to get a beat on what, Japanese imports are to the US. Next slide. And we're also doing container counting. And so this is a container terminal, as well as rail cars, where we're detecting those. Next slide. So how this fits in with Google is that we, as well as other major tech companies, have a lot of data when it comes to secondary and tertiary sectors of the economy. When it comes to retail, when it comes to shipping, there's a fair bit of data there from things that we've heard about already, whether it's social media, or mobile technology or the like. But where there is a big gap right now is at the base of the economy. And when it comes to extractive industries or global shipping, there really is a big lack of transparency in those markets and industries today, and a huge opportunity to gather that information. And so that's where Google sees this capability in the future as a way to harness that data and make it accessible to all users, not just a small set of government analysts or a few highly trained GIS specialists. So for purposes of this pilot project, assuming we were able to focus on oil tanks, and the reason we did that is we wanted to focus on what is an indicator that is important for a lot of countries that don't have good data today. And there are a lot of oil-dependent countries around the world that public statistics right now really aren't that valuable. So go to the next slide, or aren't that accurate, I should say.
Thank you, Patrick. I guess you're starting to get a sense of what's able to be done out there with some of this data, not only today, but in the coming years. I'm now going to call on our friend here, Juan Munoz, who's from INEGI, who spoke yesterday, so I won't introduce him in too much detail, but he's going to provide, in some more detail, something he mentioned yesterday was the analysis on the rural-urban systems, and another example on some historic climate data and how that's been applied in Mexico. So, Juan, thank you very much.
About the historic climate change, it's about how to use the climate data that we have to characterize watersheds, soils, kind of vegetation, land use, I'm running, and to apply different scenarios to possible changes. It's about ecological accounts, new kind of statistics that we are generating. The relevance, well, it's relevant. It's part of the of each asset that the country has. The ecological assets are very, very important for us, and we are taking care of them, taking care of how we use them, how we are trying to conserve them in the best way. So we have made some studies, taking a lot of historical information, and one thing that I need to say, maybe you are hesitating about, is this really big data? Well, take in account that we have 2 million square kilometers just on land. If you take the seas of Mexico, we have 5 million square kilometers. So each pixel represents for us 250 square meters. Yeah, we can take more in deep because we have information for each pixel with more resolution, each pixel representing 40 centimeters. But it's too much to process. So just imagine the combination that you need to do with each image. Okay, we have 1,800 historic image of Mexican territory, which can provide us information from more than 50 years to see what has been the change of the weather, of the climate, of the rainfall, and so on. So this information can help us to anticipate to the changes that we are going to have in the next years. And I'm going? Okay. It's just the last slide. This is the average that we have from 1971 to 2000 on precipitation, and applying the models, international recognized models, we have this change on the precipitation to 2099. This is about the rainfall, the average, and this is the temperature. How the temperature is going to rise in the next year.
In principle, I have two questions. We've seen very interesting presentations, and especially the last one was about combining satellite imagery with other data sources that have a certain georeference. What are the potentials in that? I think that probably this should be followed up in the future of combining different data sources that could enhance the information that we get. What are the potentials in that? And the second one is, so far satellite image interpretation and classification has very much relied on multispectral images. So classifications of different responses of the electromagnetic spectrum. I think that in Google you are probably profiting from your experiences with feature classification of images, so Google, the Google self-driving car, for example. And in your presentation you made some points on feature extractions. How could this be combined, so the feature extractions with the multispectral image classifications to produce better results?
Thank you for a great panel and a great set of presentation that really speaks to the point that you make, Greg, about the clear opportunity in front of us to start harnessing this information in a very good way. I really enjoyed it in the sense that, closer eye, I really enjoyed the various sort of presentation, but I would like to draw the attention to the world of official statistics that would like to work out of a standard. And that we have a standard methodology in which we're going to basically harness this kind of information as it comes to us. I didn't hear anyone speak about the system of environmental economic accounts, and particularly the work on experimental ecosystem accounting. We are at the forefront of doing a lot of work on this experimentation in many different kinds of environments. And in that, there is a need not only to develop, an international comparable methodology around that, but particularly also, for instance, thinking about the theoretic spatial unit model that we are developing, also understanding the international classifications that have to be improved in terms of land cover to allow this information to be more comparable, and so on. So if you look, for instance, by way of example, in terms of crop production, that definitely speaks to the point of provisioning services of typical land that it provides, but it has to be understood in the total sort of land cover that you have in the spatial unit of the country. So my point is basically also how do we actually bring that into the official statistical domain more systematically, agreeing to a common standard in which we're going to operate, much more systematically think about in developing statistical production process that are metadata driven, so that we develop a metadata catalog, and out of that we start to develop things. I see snippets of that in the presentation, but I do not see that systematically being developed. The same thing is about harnessing the information of Google. It has to be well understood what sort of information will be there to allow us to be part of that metadata catalog in which we bring in these variables more systematically to derive our sort of information. What we see a lot in this area is that there is a posteriori sort of work in terms of classifying the information and getting to do something with the data, rather than a priority thinking about what do we actually want to measure for what objectives. Now, the national accounts, so to speak, the accounts for the nation have a particular objective, and we can work with you in terms of determining the kind of objectives that we are trying to achieve, at least for a measurement of space in terms of quote-unquote a broader measure of GDP. So I think I would like to have the reflection of the panel. I know some of the countries that are on the panel actually have known and do know about the system of environmental accounts, and I really would like you to speak to that point, because I think it will help us to moderate our discussion much more systematically than we do at the moment.
I think in the area of feature extraction and classification, there are many other approaches to this. For instance, you can also do a different approach, which is that you collect spectral libraries of all the phenomena of interest. For instance, we have 100 million spectra of wheat growing under all circumstances, with pesticides applied, herbicides applied, genetically modified organized GMO wheat, non-GMO wheat. There's a phenotyping study being done. So we have spectral libraries of these phenomena, but also for seagrasses, also for crops, for forests, for building materials. In other words, you can also do it differently, which is you can do spectral matching. So the more spectral bands you have, as we will have in the future, rather than doing some kind of object-based image analysis, you can also start matching spectra and then identifying immediately what it is and its components. And it's actually developed from mineral exploration where hyperspectral remote sensing has been used now for 20 years to find ore deposits. And that's now being used everywhere as well. So it's a totally different approach from a statistical approach. And we need to merge these different methodologies, because then it becomes diagnostic, and you can do feature extraction, and you can characterize the substance, and you can, in the case of vegetation, determine its condition. Is it stressed or not? Because it has a spectral response.